Let's apply Poisson's equation to a parallel plate capacitor to find the electric field intensity and electric potential fields. In the region where you apply Poisson's equation, you have to make sure that the permittivity is not a function of position. In this example, the region between the plates is filled with one material, so the permittivity between the plates is not a function of position. With the voltage applied, the top plate will charge up positively and the bottom plate negatively. The electric field intensity will originate on the positive charges on the top plate and terminate on the negative charges on the lower plate. We are going to assume close plate spacing so that the fringing fields are a negligible contribution, and so we will approximate the electric field intensity as only in the y direction. We have Cartesian symmetry, so we'll work in the Cartesian system. These dashed lines represent equipotential surfaces. They're perpendicular to the electric field intensities, so no work is done when you move along these surfaces. So the electrical potential will not depend on x or on z. So here is Poisson's equation, and we're going to apply it in the dielectric. The only free charge in the system is the free charge on the two capacitor plates. So as long as we're in the dielectric, rho sub v is 0. So that is when y is greater than 0 and less than 0.001 meters. This is a second order differential equation, so we will need two boundary conditions, and we have those two boundary conditions. The potential at y equals 0.001 meters, which is 100 volts, and the potential at y equals 0, which will be 0 volts. Now let's look up the form of the Laplacian in Cartesian coordinates. So here I've inserted the form of the Laplacian of v in Cartesian coordinates, and since v only depends on y, the derivative with respect to x is 0, and the derivative with respect to z is 0. So here is our second order differential equation for our potential, and here are our two boundary conditions. Integrating once, we get the partial of v with respect to y equals a constant a. Integrating again, we get our potential is equal to our constant a times y plus our second constant b. Putting in our first boundary condition, we see that b must be 0. So now let's put in our second boundary condition. So then we can solve for a and obtain 10 to the 5th volts per meter for a, giving us our equation for our potential field. So when you put y in terms of meters, you'll get your potential in volts. To obtain the electric field intensity, we just have to take minus the gradient of our potential field. Here is the form of minus the gradient of v in Cartesian coordinates. Since v is only a function of y, the partial of v with respect to x is 0, and the partial of v with respect to z is 0. So substituting for v and taking the partial with respect to y, we obtain the electric field intensity to go along with our electric potential. So the electric field intensity is 10 to the 5th volts per meter in the minus y direction, and the potential field is 10 to the 5th volts per meter times y. Now that we've seen how to apply Poisson's equation for a simple parallel plate capacitor, let's look at a more interesting configuration of our two conductors in the next video.